This session is about matching your supply to the device that you want to use, because it's not always going to be at the voltage you require. For example, we have a standard 12 volt supply in most layouts, but this particular motor expects to be fed anything between 1 volt and 6 volts. And you might find by practice that the water mill or windmill or whatever device you're using requires the motor to be run at 2.5 volts or 4 volts or some intermediate value that's not 12 volts. In fact, some motors that I have in my box behind me will run happily at half a volt. So how do we get from there to here? The simplest way is to put a dropper resistor in series with supply. So some of the voltage is across the motor, but the bulk of it is across the resistor. The problem with that is that the voltage appearing on the motor will depend on the current. So if the load on the motor changes in any way, the current drawn will change. And of course, that means by Ohm's law that the voltage across the dropper will change. And so the voltage on the motor alters. So we don't get, in other words, a steady, continual DC voltage on the motor. If we're lucky, we can use a traditional voltage regulator. The image shows a very well used one called a 7805, which will output the 5 volts regardless of the range from about 7 volts upwards. And you'll see there that they come in 3 volt, 3.3 volt, 5 volt, 6 volt, 9 volt varieties. So if you're lucky and your motor or whatever device is will work happily at one of those, then that's the way to go. Just that device with a couple of capacitors either side of it, small component count, and you've solved your problem. But what if it's 2.5 volts or 1.5 volts or some other value that's the optimum you require? What are the options? Well, another simple solution is to use diodes. As you saw, traditionally we take the middle pin of the regulator down to 0 volts, but in this case we're taking a diode between the middle pin and 0 volts. So the diode is going to drop about 0.65, 0.7 volts, and that raises the output from 5 volts to 5.65 or 5.7 roughly. On the right-hand side, we've got another 3.3 volt regulator. And again, we've taken the adjusting pin not to 0 volts, but to 0 volts via a diode. And again, it raises the output by 0.65 or 0.7. So instead of 3.3 coming out, we get 4 volts coming out. So we can increase the voltage that way using diodes. We can also decrease the voltage using diodes. Like this. Here's our 7805 once more, which should normally have 5 volts coming out of the output pin. But before it gets to the device, we've inserted a diode. And as you probably know, regardless of the amount of current flowing through a diode, it will always drop that same 0.675, 0.7 volts. So as long as we don't exceed the current of the diode or the 7805, we've dropped the 5 volts down to 4.3. And that's fine. We can use these methods if the required voltage fits within these boundaries. But one of the members bought the speed controller, and that allows you to have an output range from 1.25 volts up to 12 volts. And you can just tweak the value to get what you want. It uses a LM317 regulator. It's got an input pin and an output pin as normal. There's a pin called adjust. You can put in anywhere between 3 volts and 40 volts as an input. And the output pin value depends on the voltage you put on the adjust pin. Also 1.5 amps, I'll come back to that later. As you'll see, there's always a 1.25 volt drop between the adjust and the output. And that's why the minimum output is 1.25. There's a way around that, as I showed you earlier, by putting a couple of diodes on the output. We should drop it by that amount. So instead of going between 1.25 and 12, it would go between 0 and 10.75. There it is on the little kit, just a piece of variable board with a very small component count. It's got 1, 2, 3, 4, 5, 6 components on the board. And a trimmer, they adjust with a screwdriver to decide what the output will be across these 2 wires. But the member wanted to have a fixed voltage rather than using the pot, and he asked how that could be achieved. This is a circuit, and we have 2 components here, 2 resistors, one fixed and one variable. The junction of the 2 resistors will fix a voltage on the adjust and therefore control the output. Adjusting the trimmer changes the voltage here on the adjust pin and changes the output as well. Also, it's input and output capacitors as normal. Oh, there's a diode across it. And what's it there for? Well, on the rare occasions that this capacitor is fully charged at, say, 12 volts, and there's a short at this end, the capacitor will try to discharge itself through the LM317 and blow it. So this is a bypass capacitor. It's got no effect normally. It's only if there happens to be a reverse current that will save the LM317. So if you want a fixed output, the easy way is to adjust this trimmer until you get to the speed you require from the motor, and then measure between this and here and get the resistor value and replace it with a fixed resistor. In my example, I've used an external pot rather than a trimmer. So the idea would be that these 2 are going to the pot, tweak it till you get the appropriate voltage out that you require, disconnect the pot and take a reading between the 2 pins. And that value you read with your meter is the value you want to insert between these 2 points here. And you've now got a fixed voltage. That's one way, just by doing a test. The other way is to do a calculation. The voltage on the output here is determined by, remember that 1.25 drop, times 1 plus the ratio of these 2 components, R2 and R1. Let's take an example.
Okay, let's do a very simple example. That's the formula. Let's assume that we made R2 and R1 both the same value. So that'd be 1 plus 1. So it's 1.25 times 2, which is 2.5 volts.
Now that's fine for a simple one, but when you get to different values here, you have to do a more complex calculation. Or we can take the simple route and use an online calculator. If you type that in on a browser, it will pull up a ready-made calculator. There we have our R1, R2 again, and I've made them both the same this time just to show, yep, the output is 2.5 volts. But you can do it in reverse. You can say, if I put a 470 in there or 1K there, whatever, what value do I need to get whatever you put in here? So if I put in, I want to get 1.5 volts with 470, hit the calculate button, it'll tell me the value that I require here. Here's an example. But I've put in 470 and 270, and I get essentially a 2 volt output. Bear in mind, of course, that the 470 we're looking at and the 270 we're looking at are preferred values. They've got a certain tolerance. You're unlikely to have exactly 470 ohms in your resistor. You're not going to have exactly 270 ohms in the other resistor, so you're not going to get exactly the value you see here. But within those tolerances, you can use a calculator to find out what you'll need here for these two components to get the output that you require. Now, I mentioned earlier that this LM317 can handle up to 1.5 amps. But as you saw, it's got a metal tab like most voltage regulators to fit a heatsink. Why? Well, let's look at the calculation. The power in wattage that will be dissipated in heat by the LM317 depends on the voltage in, which will normally be 12 volts, and the voltage out, times the current that the motor or device needs to draw. If we have a small voltage requirement here, they're going to have a bigger drop over the LM317.
Another simple example. This is the formula. Let's assume we're putting in 12 volts, which is probably normal. Let's assume we want to have 2.5 volts out. And if the current's low, doesn't really matter, but if you've got a high current, let's say we've got 1 amp, then we've got a problem, because 12 take away 2.5 is 9.5 times 1, which is 9.5 watts. In other words, about half or more than the power of your own soldering iron.
And that's why we require heat sinks. Depending on the current that's going to be drawn, you can either have a fairly simple aluminium one with a small amount of fins to dissipate the heat, or in this example here, the LM317 is bolted onto a much larger heat sink, more metal, more fins to dissipate the heat. And in that way, we can handle even large currents with small voltages if that is what we require.